dear ladies and gentlemen, I prepared first of the examples is pre-tension prestressed beam. I wrote a very short tutorial, or better said handout, for the presentation. In fact, I lecture at the university prestressed concrete, I used the example which I give to the students, but I think it can be used also as a general introductory example for the use of IDEA StatiCa prestressing. You can see the file which we will upload to our web, including the recording of this webinar. And as you can see, we have the design pre-tension prestressed beam according to Eurocode. This one is not correct according to Eurocode. The span of the beam is 15 meters, and we have also other data given in the specification, which I will show later. I will not be going through these handout sheets. I will switch directly to the program, and I will show you how to input such beam. So I start new task, new project, and we have a wizard which can help you to input the geometry and some loads of the structure. So we are going to analyze prefabricated concrete beam, and the concrete will be pre-stressed, and there is an option of subsequent post-tension which we will not use at the moment. We will have a single span beam, and here we have beam alignment and support positions. Once we fill in the data, we can press the button next, and we can see that the program asks about if the beam is straight or if it's curved in a plane or in elevation. What is the length of the beam? As we have 15 meter span, I assume overhangs at the ends of half meter, so it will be 16 meters together. We will want to use the standard Eurocode. We can also use some national annexes, but I will keep standard today. Our design working life is 100 years, and even if originally the beam was bridge, I will skip it now so that I make the example very simple. You have to input some cross-section. Today we will use this type of I shape with haunches, and you can adapt the data. Here the dimensions 350, depth will be 900, this is okay, 30 and 190. So that was the cross-section which I would like to analyze. Concrete grade is 50-60. Then we have to decide if we want to generate the cell weight of the beam according to cross-section automatically, permanent load, and some variable load. This is substitute variable load. I do not want to use these features of critical patterns, and I can go to the next table, and this is these are construction stages. These construction stages I decided to also to make very simple, only casting, pre-stressing. I will skip storage yard and transport for the time being, and final supports. I start with 28 days, and I will come back to that during the presentation. Final supports I assume at 60 days, superimpose dead load at 120, and this is end of the design working life. You can also change the cantilevers at the end of the beam, but as I tested the example before the presentation, I have all the data already finished, already specified. I can finish it, and now the program generates basic data. You can see that we have a beam with the cross section. We have some standard data of the project. You can also see the cross section here, materials, members, and other parts which we will come to these members and haunches later. So as I said, the program generated not only geometry but also loads and combinations. You can see now that we have cell weight, some dead load G. The number in the bracket means that the load is applied in second construction stage, pre-stressing, and some life load or substitute life load. Program generated load groups, variable and permanent, and we can just correct one data. That's the additional dead load, superimposed dead load, applied in the construction stage 5, which is, you can see the tooltip final supports, and that was -1, and actually this load was the load between in the joint between the prefabricated beams along the length of the beams. As I mentioned, I can add any point load, point moments, all these types of loads, also user-defined loads using the table copied from Excel, for example. This is very useful feature for the import of the forces calculated in some other software, or just the forces which you consider useful for the analysis. Program generated a combination. You can see fundamental, characteristic, and frequent and quasi-permanent combinations. All of these combinations are code combinations. That's why if we see the combinations here, there are coefficients 1, but it just means that the load cases are present in the combination, and the program will generate the factors according to the code. So I will explain the structure of the combinations later. I will just change here intentionally the combination to 6.10. So it will be generated according to different formula. Now we can go to construction stages. I will skip setting. You might have noticed that I go through navigator from the top to the bottom. So if you don't really know what step should be next, and you can go down in the navigator. Here we can see the construction stages. Casting, the beam is green. Transfer of pre-stressing, we skipped storage yard. Transport, we can just check on this checkbox to get storage yard. Final support, superimpose dead load. If we switch into load history here, you can see a graphical tooltip. Then you will see that principle of how we combine the loads. For example, the stage final support, which I have mentioned, is the stage here in 60 days. And at that time, the program applied R5, which is rheological load case, in which we store the effects from stage 2 to stage 5. You can see here that the load cases are R5 or G5, and also this G5, which was this additional superimposed dead load. So in these load cases, we store the increments, and if you sum all these load cases, you get the total value, which is the result of the combination, and it shows you a total structural response of the structure on loads applied in individual construction stages. This is the principle. Now we can go back to load cases just to explain why we didn't show these relogic load cases. You can press it on and you see that we have also R, G, for each construction stage. You don't want to see those automatically generated load cases, you can switch it off. You can also explain better now the combinations, so that I will edit it. And for example, this fundamental combination, I have only cell weight, one relogical load case, one G, and pre-tensioning. But if you go to final supports or superimposed dead load or even to end of design working lives, you see that we have more load cases combined in this combination. One of them is this variable load. So the program generates these necessary combinations for you. Of course, you can add user-defined combination here with no problems. As you can see, this is quite useful because you do not need to learn the logic of the program. The program does not require it, especially as concerning construction stages and time-dependent analysis. The program generates these load cases, combinations, and model automatically based on the data you know, and then based on the data you input via tables. Now we can go to Tendon design, and in fact the program will start a separate module in which we can input both pre-tensioned and post-tensioned tendons. Now we see the module. Again, we can see this structure response in time. We can also see not editable tables, what load cases and combinations are available in these stages, and we can go further in this navigator to design members and see the design members. First of all, I would like to show that we can see plane XY and XZ. It is, you see here, uncoiled view, which means that if we have a 3D structure, then it is uncoiled into 2D, and you simply work in 2D. You can switch off on these projections, and you can also make it scaled in vertical direction. Here now we have 1:1 scale, but if we want to scale it like this, then we can switch it off, and we have really beam in which you can edit the tendon and with no problems. So when we are happy with this, we can go to tendons, and I will use the possibility to input the tendon, pre-tension tendon inline. Here in the data window, you can see our predefined pre-stressing load case. The program selected first tendon on the list. My tendon will be Y860, this one. And I can go to the definition of the geometry. I know that either from some preliminary calculation or from my experience that I will have 5 strands. Or I can simply check it, and in several minutes I can check if it is correct or not. And also I define this data from vertex 6, which is 75 and 63, and here again minus 75 and 63. Sorry, 63. And you can see the tendons here, but also we can switch into cross-section here. Here we can see only one group of the tendons, and here we see all groups, which we still don't have. We will add one pre-tensioned in line, and the number of strands will be again 2, but the geometry will be different. Here I will have again 75, 113, minus 75 and 113. And now it's okay. You can see this group. As we need to reduce the pre-stressing force at the beginning and at the end of the beam, we define blanketed length, in which we have debonded strand 3 meters. So now you see that the tendons or strands are debonded in position 0 here. And if we go back to this, I can show we go to 3 meters, then it disappeared, so these debonding tubes disappeared. So that's it. We can go back to tendon tab sheet, and we see that we have 2 tendons. The program took the same material by default. What we don't have nice is initial stress, because this low stress was selected for previous type of tendon or strand. So I select both using shift, and I edit it here in this selected tendons, and I want to have higher stress. By the way, you can see now that we have all the tendon checks satisfactory. But if I go to 148, this high stress, it is bigger than the maximum, as program gives you the 1476. Then we see the tendon stress check is not satisfactory. I will explain it later, or I will improve it later. Now we can go through this to see also force design. For pre-tangent beam, we should probably show Fx normal force and also My. We can of course show also the other components also acting in plane XY, but for this type of beam it is not necessary. Even this Fz is 0, so those are equivalent forces. And we can go to short-term losses. We see the table, summary table with checks which are not satisfactory at the moment. And here we have also the distribution along the length. Again, the check is not satisfactory. So what to do with this is that we have to check, change the parameter in the code. The code is in the parameter, we can filter it, of course. We have filters here, but I know that it is in chapter 5, and it is parameter K2. You see 510 to 1, and we can improve it, increase it to 95%, which means that based on the Eurocode, that you can do it in the case that you measure the stresses in the factory with certain precision. So in that case, we can go to higher level of the stress, and you make your design more economic. Now we see that the check is okay. By the way, here I can see also info window, which I haven't mentioned yet. There is a status about what is imported from the beam. If there is some problem, there will be a cross instead of this Nike. The program tells us the length of the beam is 16 meters, tendon length is 112, tendon mass together 132, and tendon mass per cubic meter is 28 kilograms of tendons per cubic meter. And also some other useful information in these windows about current tendon and so on. We can also go to design member results, but I would have to calculate. You see that it became red. We would have to run finite element analysis. Instead of that, I will exit this module, and I will go directly to the beam, and I will calculate time-dependent analysis. In fact, now the program calculates all the construction stages, including these sub-intervals necessary for proper analysis of creep, shrinkage, relaxation, and aging. The program calculates it for all combinations which were generated before. Now we can go to, let's say, at least internal forces to see what are the internal forces. We select, let's say, ULS fundamental combinations, and you will see that we have such distribution of bending moments. You see bending moments for all construction stages and all ULS fundamental combinations. If we want to go to casting, then there is nothing, no force, because the concrete is fresh, and this is Selvey. Then we go to transfer of prestressing. Already we have some scatter of the moments, some differences. We go to final supports, then it is even bigger. Superimposed dead load, the moment increased here, and also end of design working life, you see different forces. You can see these forces in detail in the table here. Also, here you might notice that we have a factor 1.35 for cell weight, 1.35 for G2, which means this is the combination for ULS fundamental combination actually in construction stage 7, this index 9, which was identified as a critical for certain internal force. So you can search it here. When we have it and we are happy with the results, we can go to concrete design. First of all, we can mention that all these exposure classes and other data can be adapted. Also, checks can be selected which one we want. But we have to define reinforcement zones. For pre-tension beams, usually we have same reinforcement along the length. Possibly the shear reinforcement above the supports will be different, but for simplicity I don't mind at the moment. I simply want to check it in positions, and the first generated position was 8 meters, which was in the middle. As the program generates the sections according to both geometry and the loads which are applied, I will use 7.99 just to avoid the case that in the middle the program generated very small point load caused by the tendon due to some effects which we cannot explain here, and now I avoid to generate two load cases, two positions, one just before and just after mid span. Second section would be at above the support. I am using the position 1.3 meters, which is at approximately the dimension D, which is you see 900 millimeters minus some concrete cover and centroid of the reinforcement. If we add 0.5, we approximately get 1.3, which is the section in which we should check it according to Eurocode. Once we have it, we can go to detailed analysis, run detailed check here, and the program runs again the module, which works also as a standalone program. You can see this IDEA StatiCa. If I open it, you can see we have, sorry, this is, I can switch into different language. We have English, Czech, Slovak, Dutch, German, Polish, and Italian language. And if I start it again, I have to start it again. Then it will be in English. And you will see that RCS is a standalone concrete, or in pre-stressing we have RCS, standalone reinforced concrete section program, which we also linked to this beam program, and the program generated the data for you. You can see two sections at 1.3 meters and at midspan, and also several extreme name, which are in 28 days, 60 days, 120 and 100 years. Also in each extreme you see one ultimate state combination, one serviceability, three serviceability, one characteristic, frequent and quasi permanent. So we can immediately start calculations, and the program ran these two sections in all these extremes. You see that in the first section above the support we have here unsatisfactory shear because there are no stirrups. In the second section we have unsatisfactory even the capacity, about 10% more, and as we check also the interaction of all internal forces, and the interaction calculation is based on the response of the section, and the response was not found because of not sufficient capacity. Then we put there 1000%, and it shows you that we did not find even the response. It means that we have to reinforce the structure. Before I do it, I can show you also these design members which were filled in this module, reinforced concrete sections. Then in design we have cross-section pre-stressing. I can show the construction stages. You cannot change it here because it was done, and I can show this on this axis. Yeah. If we have a composite section, then the cross-section changes, action stages, all these data imported from also internal forces from the beam. And now we go to reinforcement. And I use the template, and I will use 4 bars in the top 10 millimeters, 0 bars because I have already these strands, 1 bar in the middle just to reinforce the reinforcing cage, stirrups diameter 10 millimeters, 45 millimeters stirrups cover, and I will use stirrup distance 0.15 with the overlap 200 millimeters, and we will see. I will remove the dimensions. Now the program generated these stirrups, and we can go back to sections and we can calculate it all. Now we will see if it improved, and it seems that it did. The non-prestressed reinforcement improved the capacity by, let's say, 9%, which is not satisfactory. We have still 101, and here we have 107 for shear, which is still not satisfactory. I could change maybe more, put there more reinforcement or other things, but what I wanted to show intentionally was that I go to combinations, and I will change it from 610 to 610 AB. Of course, because we have to regenerate it, I have to recalculate it again. And I want to just to highlight the fact that according to Eurocode, if you use this combination 6.10, it is not as economic as 6.10 AB, which you will see in the program. Now we go to reinforcement, and again detailed. I run it again, and we see that it will be much better. This is at midspan, it is even satisfactory. And above, and we can also see which one was, you see it is 94%. We can go through all the all the checks. And we see what is the capacity, and the biggest was 94.5, so it improved significantly. And this one, this shear still needs a little bit more. I would don't care about 0.7%, but if you really want to be strict, then we go to reinforcement. We select the reinforcement, and I will change from 150 to 140. And also the other stirrups, just because I want to have it nice in the report, stirrups in the same positions. Of course, if I wanted to have different distance of stirrups above the supports and midspan, I can do it by defining different zone of reinforcement. Now you see that we have it finished. All these calculations are done, and it is satisfactory. We can see brief report, each section only one row. Standard report, usually in pre-stressed concrete it is a little bit more than one page, in non-pre-stressed it is one page. Detailed, which generates all the pictures and all data, tables, intermediate results. You can see the reinforcement, interaction diagram, torsion. There is no torsion here, but we calculated as it was required by the user. Here also the distributions and other things. You can, this detailed report, you can set in here what tables you want, in which section, which checks you want, and in checks, for example, what explanation or non-conformity tables and other things you can set it. So I will cancel it now. It seems that we finished, let's say, in a quite reasonable time the design, but I admit that this design would not be acceptable in practice because of this data. Here we have 28 days transfer of pre-stressing, which is not acceptable in a prefab factory, and usually we can, or the user specifies the concrete strength at which we have to, or we can pre-stress it. So then we can put here 25 megapascals, and the program automatically calculated an equivalent age of the concrete. You can see also the tooltip here, what the program in fact calculates. This 1.9 is still quite long time. It should be less than 1 day, definitely, I know it, but it is equivalent time, okay, equivalent age in which the concrete would mature to the same level, to 30 or 25, now 25 megapascals, when we have 20 degrees of Celsius. If we have some heating of concrete, of course it is less, but we work with equivalent time. Of course we lost the data, so then we have to recalculate it. By the way, if you input this 1.9 days as the age of the concrete, then it is not allowed by Eurocode unless you check also this really test the concrete strength. So the program would not allow this case if you do not specify this value. So we can go back to reinforcement, detailed, and if we calculate it now, we will see the results, and we already see that stress limitation is not satisfactory at the time of pre-stressing. practical beam. So I go back to the beam, and why did I say practical, almost practical? I have no diaphragms above the support, for example. So I wanted to have this input very simple, so that's why I didn't bother you with this problem, but we can solve it very easily. I can save it and probably save it as, because I spoiled the data, 310 like this. And I will add the cross-section, rectangular cross-section, and we see that the depth is 900 millimeters, the width is 800, so I will put here 900, here 800 millimeters, same concrete, okay. I have another cross-section, and for example here I can change it into the other cross-section. That would not be nice because of this support. So if I want to have it in the middle of this, then I say, okay, I will change this to 0.25. I will here 0.25, and here I will keep this 15 meters. Sorry, not 150, but 15. And also the support here at node 3, I will switch off the members and now node numbers. So node number 3, and now last change will be rectangle. Now I have it as I wanted to have it. Of course, I can do it also in the other side of the beam. If I want to make it haunched, then I go again to cross sections. I select this ice section and I copy it. Once I copy it, I have all the parameters same, but I want to have, for example, the depth of the beam 1.4 meters. I go to members. I select the span which I want to make haunched, and I go to symmetrical. And first I should change the cross section here to the big one. And you see already we have it here, but the length of the haunch is not correct. It should be 7.5 meters. Now I have it, but the other way around. It's upside down. I have to go to project data, and if you remember the wizard, we selected that beam alignment should be to top surface. Now we select bottom surface, and we have it as we wanted. And the only problem would be that here we have constant cross section, so probably we would have to interpolate and to adapt the depth of a rectangular cross section. Before I go to other example, I just want to show you one, you would say, unpleasant feature. Of course, if we entered the tendons earlier than this haunch, then the tendons, the program gives us that the tendons are outside of the cross section. We go there, we will see this, I would say, disadvantage, but it's clear that the program did it in correct way. We go to tendons, you see that it is outside. We go here to pre-tangent group because it was related to this vertex number 4. So you see it is here. We can also check it in cross section. We go to the other position. Now the beam is increasing the depth and decreasing the depth. In other position, we can go to 3D and check what about the geometry and correct it. So that's I wanted to show. Of course, if we use templates, for example, for non-prestressed reinforcement, we can do it with no problems relatively to the cross section. Now I will, because this example is finished, I believe, I want to show you. I save it and I start it again, beam. And I will show you some other example of real practical or real life, I would say, beam. It is this one, saddle beam. I open it. And you will see that in this case we have this interpolated as I explained. At the end we have different cross sections. We have this change of the cross section. Maybe I can show it in a tendon design. And program again gives us the warning that they are outside of cross section. I will show you why. It is because the width of this flange in the bottom is smaller than the width of the flange at midspan. So we go to tendons, then maybe I can go directly to 3D. And you can see what is the problem. The tendons here or strands here are outside of the cross section. We can show it also in cross section. Here we have it. Of course, there is even debonding, but it is not in the cross section. If we go to different position here, already we see that we change the cross section, and also there is a debonding of these strands, and we go further, and again the beam increases and goes back. I exit it. And just to show you that we can analyze this, the program again gives us the warning, so I don't mind. I know that it is intentionally, or the input was intentional. So we go to the reinforcement zones. And here we have plenty of sections defined. For prestressed concrete, it is much better to check the positions in this bottom table rather than to this one in the reinforcement zone. This is more for reinforced concrete. If you do it, the program calculates it, but you, for example, in post-tension beam, you do not know exactly which section we do it, because we do it for the zone. Okay, so it's better to use this one. If I go to detailed, all these sections will be generated in this RCS module or RCS program, and we can run it. Of course, we can see here this is much more complex in the construction stages, so you see plenty of construction stages, and some of the checks are already finished. You will see that it will not be satisfactory in all sections, especially here above the support. We have shear 1% more. But this is a question if the user, this is a project from the user probably expected that this section would not be necessary to reinforce more, because there would be a reduction of shear force. But what I wanted to show you was the design, and here the reinforcement. Now we are in just above the support. You see the tendons outside of the section. Program tells you. If we go to the other one, 1 meter, then we are already in I section or with white flanges. And this one is the generated section. This is the original one, and this is the one which is at the section. We go to 7 meters, you will see the difference in the depth. So this we generate, and you see that we also adapt the reinforcement, because this reinforcement was entered or was input as the reinforcement, and here we have even bigger as the reinforcement as from the template. I think we do not need to see the results. I can open last example. I hope I did not forget anything. I don't save it, and I go to composite continuous bridge. It is a part of the bridge, only one beam of bridge. You can see here composite section. Here we have composite slab, 3-span beam. First, what I want to show is the member history, because you can see that we have different members in this 3-span continuous bridge. First member, number 3, is this one, and the member has its own history: casting, transfer of prestressing, storage yard, transport, I'm changing this, temporary supports, casting of composite slab. By the way, here we can define internal temporary supports. If we want to have required camber by value or by fracture, we can put there 10 millimeters or whatever. But in that case, it's such quite a small beam, is only 13 meters or 12 meters span. It is quite stiff, and it would not be satisfactory. So it is not recommended, I would say. Final supports, superimposed loads, and end of design working life. For this member, we go to construction stages for the whole structure. Then we can see similar construction stages, individual beams, changing of boundary conditions. You see now it is pre-stressed. This one is already on the stock. We have different ages of each beam, each prefabricated beam. Storage yard of the second beam, casting of the third beam, again transfer of prestressing, storage yard of third beam, temporary supports, casting of composite B slab, final supports, superimposed load, end of design working life. So this one is quite complex structure. We can analyze in a proper way time-dependent analysis, including this creep, shrinkage, relaxation, and aging effects. And we can go to the checks, and that will be the end of the presentation, in which I will show you the response in individual construction stages. So let's wait for the program. And we have plenty of sections, plenty of beams, different ages. So the number of finite element analyses which we do is quite significant. So when we finish, then we go to the reinforcement, which I have already prepared. Here we are. And maybe I will, it's enough if we have one section only. I will start detailed. And when I run it, we have only section at midspan. You see this is our reinforcement. By the way, this is combination of pre-tangent and post-tangent beam with the duct. I will show you later, I forgot it. And checks, let's say I go to response, and I will make the picture nicer. Here we have a transfer of pre-stressing, one extreme at 2.9 days. If I select the other one, then the program changes the response. Now we are on storage yard, then temporary supports, the other temporary support for other beam, casting of composite slab still does not exist because it's soft. The other beam, the other extreme, sorry, final supports. Now we have already the slab, final supports, post-tensioning, superimposed load, end of design working life, and end of design working life other extremes. So that's it. You see that now the slab is completely in tension due to shrinkage, especially shrinkage of concrete. I told you that I forgot. I promised that I will finish, but I think it would be nice if I show you the last picture in tendon design, which I forgot to show you, and that is the combination of this pre and post tangent tendons. And there is one feature. You see that these construction stages are quite complicated. We go to tendons. We have here the post-tensioning tendon, also the groups of pre-tensioned strands. But what you see here are tendon spacers. I can set different levels of tendon spacer, and the program calculates at which distance from the beginning of the beam you should put which spacer. Here, for example, you can make this geometry of the tendons a nice way, and then to export it to DXF to have a draft drawing of such tendon or the other tendons too. I think that's all for the presentation today. I thank you very much for your attention.